Hi, in this video, we want to take a look at the impact of the number of levels when we're working with Gower's distance. Okay, so remember in Gower's distance, we're going to get back a distance matrix, and it's measuring the dissimilarity between all of our rows of data. So each observation is compared to each other observation in the data set. And something that's very nice about this is that Gower's distance can handle any type of data. It can handle numerical, ordinal, and categorical, nominal. So that's really good. But something we want to know before we start working with this is how will the number of levels we have impact our data, or impact our models when we use Gower's distance. So something to think about is, should I bin my data before I do this? How much data prep should I do before I start running this if I'm going to do like unsupervised learning? So here the focus is going to be really on unsupervised learning, clustering in particular. And that's just because that's how I usually use Gower's distance. All right, so to measure how things go with Gower's distance, we're going to look at two particular aspects. We're going to look at one, system time. Second, we're going to look at the coefficient of agglomeration from hierarchical clustering, and I prefer to use Ward's D when I do hierarchical clustering. I use Ward's D when I want to have more even-ish clusters, and I use single linkage when I want to do outlier detection. I know that a lot of people prefer complete linkage. I think that leans more to the Ward D side, but whatever. I'm pretty sure the results are actually going to end up being relatively similar. All right, so let's go ahead and generate data. So what we're going to do, we're going to generate some data. We're going to have the number of rows that we have for each data set will be the same. The number of columns will be the same. What will be different is that each column will be categorical data, but they will have a different number of levels. So the first data set is going to have 5 columns, each with 1 level. So it's going to be the constant. It's going to be stupid, but I'm running through it just so it is coherently 1 through 26. I'm using the letters of the alphabet, also lowercase. And so then the second data set is going to have 5 columns of data, and each column will have 2 levels. And then the third data set will have 5 columns once again, and each column will have 3 levels. And so I'm going to keep on going through this all the way up to 26. I'm using the lowercase letters of the alphabet to label the levels. All right, so how am I going to build this? So first thing I do is I go ahead, I build a random graph on 5 columns, so on 5 nodes. Why am I doing that? Well, I want the same structure or the same relationship between my columns as I do this, because I want to be more similar to each other for the purpose of comparison on our system time and on our Gower systems. This really isn't a big deal. The punchline was going to come after the generating data aspect. I just needed data to work with that was comparable. And so here I'm randomly generating data, and that data, along with the structure, is actually used to build the actual data. So there's kind of like 2 steps of data building. All right, so next thing I want to do, I want to go through and I'm going to use DAISY in the cluster package of R to compute Gower's distance. So I'm taking the DAISY function, I'm plugging in the data, and I'm telling it to use Gower's distance. Now, when I do this, I'm also, at the same time, I'm telling R to record the system time, and I'm just going to use the elapsed time. I'm not going to use all 3 versions. And the reason why I'm doing that is just to make this a little bit easier for me to interpret what's going on. These 2 steps, these are just about just labeling things so I can have the names in a coherent manner. And then this step is just taking the output and putting it into a data frame. So let's take a look at the scatter plot. All right, so we can see that there's kind of like a trend, and then things kind of like spiked up I think this spiking might be from me, checking the internet while the code was running. I'm not real sure, but this is a enough difference in the elapsed time that we can see that it actually kind of like went down as the number of levels increased, which was very surprising. I thought it would be the other way around. But there's also like scattered a lot, so I'm not really 100% trusting of it. But I ran this multiple times, and I got a similar pattern every time. Now for hierarchical clustering, let's go ahead and, so I'm going to take all of my distance matrices that I've generated, all 25 of them. I did that for levels 2 through 26. I'm going to do hierarchical clustering with warts D as a linkage. So this is warts D, it works to minimize the standard deviation of clusters. And then let's go ahead and plot like for 2 levels and 26 levels. Let's see what the difference is. All right, so this looks relatively uniform going up the hierarchy, right? So, in terms of like a taxonomy, it's kind of even stepping up. And because there's so many observations that, we just can't interpret anything that's going on down here. That comes from the fact that we have so many data points. But on the upper part of the dendrogram, we can see pretty well what's going on. Now, when I get down here, I can see that it's not nearly as even going up. So specifically, look over here. Look at this part. Like these are off kind of like, if I was to cut my cluster anywhere from here to up here, all of these will be off by themselves. All right, so this was a very different cluster setup. So when I look at this, I would expect like down the road, if I was working with Gower's distance and I had to choose on the number of levels, we can see that the number of levels is probably going to, if I have more levels, it's going to have like less even number of observations in clusters throughout. And you can see that specifically if I was to cut like up here. If I was to cut up here, all the data in this part, the vast majority of it would be in one cluster, and the data down here would be in a completely different cluster. Well, up here, we can see that it's much closer to 50-50. All of these observations are in one cluster. All of these observations are in another cluster if I was to cut up here. Okay, so we can see that we'll probably have like more even for the number of observations in a cluster if we have fewer levels. So this is something to think about if I'm going to do supervised learning, unsupervised learning with Gower's distance leading into hierarchical clustering. When I do my data prep, should I bin more? Should I bin less? Should I not bin at all? This helps give me insight into how to proceed. Now here, let's take a look at the agglomerative coefficient. So previously we just looked at the extreme cases where we had 2 levels and 26 levels in each column. So now I want to measure along all of them for 2 levels, 3 levels, 4 levels, 5 levels, and so on. And we can see a pretty good trend that's going down like this. Now remember that the data was generated using a random number generator, so it's not going to be a perfect line, but I'm pretty sure the agglomerative coefficient is going to decrease as we go down. So this is consistent with the hypothesis I already presented, that the fewer levels I have, the more even I can get for my clustering, more than likely. If that's important for a project that I'm working on, then I would do more binning of my categorical data. All right, well, that's all I've got for you. Take care and goodbye.